Hey there. Today we're going to explore functions and relations in math. This topic is super important because functions are like machines. You put something in and you get something out, but only one thing should come out for each input if it's a function. Let's break it down and make it super clear. A function is a rule where each input, the x value, gives you exactly one output, the y value. Think about this. You type in a number into a calculator, let's say, and you always get one answer. If an input gives two answers, then it's not a function. Let's look at this from a table. Here, we check if any x value repeats with different y values. So each input has only one output, and that makes a function. Let's look at this table here. The value of x equals 1 gives the value y equals 3, and x equals 2 gives y equals 4, and x equals 3 gives y equal to 5. Each input has only one output, so it's a function. Here, we see it's not a function because for the two different values of 1, we get 3 and 5. For the same input of x, which is 1, we get two different values, 3 and 5. Two outputs for the same input is not a function. So this does not represent a function. Let's look at this from a graph. If we draw a vertical line, and if it touches the graph more than once, it's not a function. Let's look at this. X squared plus y squared equal to 9. This represents the graph of a circle with a radius 3 and centered at 0, 0. If we draw the vertical line here, we see that it touches at this point and this point. There's two intersections, so it's not a function. Let's look at this. Y equal to x plus 1. It's just a line. And if we keep drawing vertical lines, we can see that it's only going to have one intersection. So it is a function. Let's take a look at this from mapping diagrams. Function mapping should be 1 to 1. Let's look at this. 1 goes to B, 2 goes to A, 3 goes to C, and 4 goes to D. Can't be like 3 goes to C and D. That would not be a function. Like this. 3 goes to 5, but look at 9, 7, and 8. Two outputs, so it's not a function. Let's talk about transformations. Function transformations change how a graph looks by moving it, flipping it, or by stretching it. Think of editing a photo. A shift is equal to moving it. Reflect is to flip it, and the stretch is to zoom it. Here, let's look at this. Shifting a function up obviously moves the graph higher, and we add a positive value outside of the function's input. We add it to the output. And if we're shifting down, we're moving the graph lower, so we add a negative value, or subtract a positive value for that matter, from the output. And if we're shifting left, we're moving it to the left. So actually to the input, we have to add a positive value. So f of x plus 1 was shifted to the left by 1. And if we're shifting right, we're going to subtract a positive value inside of the input. So we're shifting this function to the right by 4 points, or 4 units. And if we're reflecting over the x-axis, that means we're flipping the graph upside down, so we just take the negative of the function value. And if we're stretching vertically, which means we're making it taller, then we can multiply by some constant. And if we're shrinking vertically, or make it flatter, we multiply by some constant whose absolute value is is less than 1. And if we're stretching vertically, the absolute value is going to be greater than 1. So let's take a look at some graphs. Here's the original function, just y equal to x. We're shifting it up by 3. We see our y-intercept shifted up by 3 points. And if we're shifting it down, shifted down by 2 points. And if we're shifting to the left, we see it shifted to the left by 1 point, and here we shifted it to the right by 4 points. And if we're reflecting over the x-axis, notice how it got flipped over. Before it was like this, now it's this way. And if we're stretching vertically, here we're just increasing the slope, so it becomes more steep. And here we're shrinking vertically, so it becomes more flat. Let's talk about inverse relations. An inverse relation is like undoing what a function does. If a function takes you forward, the inverse takes you backwards. Let's look at a real world example. Let's say you spend $5 per hour at an arcade. The function is f of x equal to 5x, where x is the number of hours, and f of x is the money spent. The inverse would be f inverse of x equal to x over 5, where x is the money, and f inverse of x is the hours played. Here are the steps to find an inverse. First, we replace f of x with y. Then, we switch the x and y, and we solve for the new y. So, let's say we have f of x equal to 2x plus 3. Replace the f of x with y, so we have y equal to 2x plus 3. Now, we switch the x and y. So, x equal to 2y plus 3. Now we solve for the new y. So x minus 3 equal to 2y, where y equal to x minus 3 over 2, and that gives us f inverse of x is x minus 3 over 2. Let's talk about a different kind of function, piecewise functions. A piecewise function is like a rule book with sections. Each section has a different rule, depending on the input x. It is made out of pieces. Here's a real-world example. The cost of delivering a pizza, depending on how far the person lives. If the delivery man has to travel a distance between 0 to 3 miles, the fee is going to be $5. But if it's between 4 to 6 miles, it's $7, and if it's 7 plus, it's $10. The fee changes based on how far away you live. That's what a piecewise function does. Here's an example function. X plus 2 if x is less than 0, and 3x if x is greater than or equal to 0. Using the first rule, let's say we want to find the value of f of negative 2. Where does that go here? Negative 2 is not greater than or equal to 0, so it goes here, where it's less than 0. That's true. So it's going to be negative 2 plus 2 is 0. And if we want to find f of 1, it's just going to go here. So 3 times 1 equal to 3. Let's see this. Imagine a video game with different levels of difficulty. Easy mode for levels 1 to 3, medium for 4 to 6, and hard for 7 plus. Piecewise functions work the same way. There's a different rule for different zones. Step functions. Step functions look like a staircase on a graph. It jumps from one value to the next without connecting smoothly. Same value for a while, then a sudden jump. Here's a real life example, the bus fare. If the miles traveled is 0 to 4, the cost is 2. And if it's 5 to 9 miles, it's 3. And if it's 10 plus miles, it's $4. So if you travel 4.1 miles, you pay $3 because there's no in between. An example would be the round down function. This takes in a value of x and rounds down to the nearest whole number. So if we get f of 2.9 and pass it down to the round down function, we get a value of 2. And 5.4 would give us 5, and negative 1.2 would give us negative 2, because that's on the negative side of the graph, and rounding down would give us a lesser number, so it's negative 2. So each time it steps down to the closest whole number below it. It's like going up the stairs. You stay on one step until it's time to jump to the next. There's no sliding. Domain and range, in real-world context and abstract. So in the real life, the domain would be what we're allowed to put in and what you get out. So applied to the real world, we would see that if we're selling 1 to 5 cones per day and each cone costs $3, Then the function would be f of x equal to 3x if x is the number of cones sold. So the domain would be every number from 1 to 5 because that's what we're limited by. And the range would just be passing in these values into the function and then giving a new set of numbers. So 1 gives 3, 2 gives 6, 3 gives 9, 4 gives 12, and 5 gives 15. So our range would be 3, 6, 9, 12, and 15. Domain and range in abstract math. Let's say f of x equal to x squared. Here, we can plug in any real number. There's no limits. But squaring never gives any negative numbers. So the domain is all real numbers, or from negative infinity to infinity. And that means the range is all numbers greater than or equal to 0, because we can't get any negative numbers from this function. So the range would be from 0 to infinity, where 0 is included. This function works everywhere, but only gives positive results. So domain is what you can plug in the input x. Range is what comes out, the output f of x. In context are the inputs and outputs that make sense in real life. And abstract are inputs and outputs based on math rules. So overall, functions are everywhere, from video games to pizza delivery to bus rides. Once you see these patterns, it all makes sense. Thank you for watching this video.